Classic movement, non-classic movement, complex camera behaviors, active weapons, consumables and interface to manage all that, complex fights and flows with stances, reaction and combinations, and all that backed by an RPG stat system with resources and characteristics. Brain hurts if you're trying to imagine your character's physics update function that manages all that every frame, but studio-made games somehow achieve this, and I want to leave the curtain on how this is done. The secret is a combination of good pipelines and good architecture. This video is about architecture with an example of pretty capable controller base. It has basic movement and a framework to create a combat system of unlimited complexity, be it a MOBA, a Souls-like, or a Mortal Kombat-ish fighting. Any guesses on the length of my physics update function? 3 strings. In this video I want to gallop this structure once more to paint the full picture. For older viewers, this isn't a full content duplication video, you will find more interesting stuff as well. So how to achieve Godhood? First step is to separate your main cycle into 3 aspects: input, model and presentation. Input contains everything there is about tying user hands to your game gods. Model is the heart of your character that simulates its behavior according to the input produced by the player, and the presentation is the last component that ties your game to players' feelings. It is responsible for all the characters and weapon skins, all effects and all sounds corresponding to character lifecycle. Then we need to implement those aspects as encapsulated as possible. We want our input to know nothing about the model, so what input is doing is it gathers all input data for the frame into a package that is being sent to the model to simulate. The visuals currently are very simple. They contain 2 array meshes as a skin to our player and a skin for player's weapon. I want to highlight that it's all the visuals contain. This mesh's correspondent skeleton is not here. The skeleton of the player and its animations are a part of the model. Model is huge. It took almost 800 code strings to narrate it. It needs to have the skeleton and animation for our player, the weapon and its hitbox to provide combat glue, and it somehow needs to hold quotes the real physics update function. This physics update function is a smart task construction called state machine. The state machine states are responsible for most of the update logic. They are unique classes that have a common ancestor. This ancestor, the base state, is called move and is the single largest class in my codebase. Let's inspect it. The core are 2 functions: check relevance and update. Check relevance implements state machine's transition logic piece related to a particular state. Update implements the physics update cycle of the player during the state. Then the base move also contains a bunch of default implementations for interaction between entities in the game world. These defaults can be divided into 2 groups: reactions family and getters family. Getters are short methods that answer a question about our character state. They are so short because they are implemented with the help of a powerful animation technique, but in core they can be implemented as any getter, just return something. Reactions are methods that define current state behavior when it faced an input from outside of the player's model, some enemy or environment impact. Move airs are of course able to override these defaults. For example, default reaction on hit is to take damage and to become staggered, but shield block state can redefine its reaction on hit to pay some stamina and not get damage or stunned. Here's how the whole cycle works in short. Input package gathers player's inputs into a package and transfers it to the model. There, it is transformed, translated and filtered with any additional contextual layer you want to add to your game. My layers currently are a resource layer to work with some statuses, staminas, etc. and a combat system layer to translate input actions from one attacking button to several possible moves. When layers finished morphing the input package, it goes into current move transition logic mechanism. Transition function decide if the state wants to secure its management for the next frame. If not, it returns the name of the state that needs to take the priority from here. Under the hood, it works in 3 steps. First step is to process any queued inputs, like in the Souls series, to queue attacks during the previous. The second step is to check if you have any first moved from the past. For example, player HP got lower than 1 somewhere during the past frame. We are dying here no matter what the current state wants. Then default behavior of the current move kicks in. It is the transition logic of the state with no interference, the default life cycle. For example, midair just lingers till it will sense the floor under our feet, or an attacking move lingers until its animation is over and then transitions. After the transition, we have the state that will rule until the next frame. The next thing that is happening is that state's update function is being called. This function is usually a small piece of logic responsible exclusively for updating current things, such as moving sliding character around or managing other things dependent on timing. When the model finished its business, we are ready to present, so the visuals can be called. But the visuals are a strange beast. They can use some physics updates, but they also can perfectly exist using simple process. Right now we have little use for it besides snapping the weapon visuals to the weapon model constantly, and the array meshes of skin for our skeleton are updating themselves automatically. We only are showing them the skeleton on the start. Now, what's the actual point of this video? First point is this video is the condensed 10-time content of my character tutorial series. I plan to create at least 2 more series in the future, one about creating enemies and AI, and then a series about building a proper multiplayer. And instead of building those in a vacuum, I plan to use this project as a starting point. I can just say, yo, to understand me, please watch a 17-minute character manual, so I have created the 6-minute version. The second point of this video existence is my marriage. 1st of June, I am marrying the love of my life, and I want to limit my presence in the reality for a calendar month. For the channel not to rot completely during this period, I will plan and release several smaller videos. They will be based on this controller tutorial and will show how to implement nice different features without the extensive commentary, just with a short algos overview like here. I will call them something like Mechanics Museum. Essentially, this will be an easy to follow popcorn content about this controller base flexing its muscles. If you have any suggestions in mind, write them in the comments. I am currently aiming at nice inertious movement with not instant turning, better controlled jumps and tracking ability from Dark Souls. It's the ability to change attack direction on the fly after the attack started. If I will manage to deliver it in time, there will be a video about parkouring, ledge grabbing, wall running and whatnot. It seems people are interested in ledges for some reason. If you are from the future, you can end here and return to the Mechanics Museum video. Or you can watch the 70 minutes version if you really want to open your Godot's chakras. Now, for older viewers, I want to highlight changes that came with migration from the version 4 to version 5. Nothing conceptual is changed, but there were several rounds of refactoring turning this basin into a truly polished gem. The biggest change is my move doesn't have priority dictionary and sorting, and also my model doesn't have moves registering dictionary. To escape having 200 strings manual appending dictionaries, move class now has a name field and a priority field. The container node now has the function of registering and sorting moves and providing them access to models fields, sort of shielding them from the model. I also cleaned up my states a bit, showing maximum amount of functionality into defaults and backend animations. Now the whole queuing system works outside of moveSci in the base transition logic. This is achieved by having 2 backend tracks, accepts queuing and transitions to queued. I also flipped the order of checking for forced and for queued moves. Now the algo is as follows. First we check combos if they want to queue. Then if the state can transition to queued moves, we don't transition to it. Instead, we are trying to change our long stored queued move into a forced move. Then we are transitioning to forced move if present, and then if not, we call default lifecycle. Speaking of it, default lifecycle now also has a default implementation. This default implementation suits for simpler side animations that have a default that just lingers until the end of the animation. This allowed me to delete this function from all simpler side states. It's actually quite funny. Look, I have a stagger reaction on hit that is a move air, but now has no code in its script. It is literally fully covered by just base moves export parameters from editor and a backend animation. Similar to this, parry, parried, def, etc. If it just waits, it doesn't have code. I also deleted and unified the scripts of an attack. Now the attack is a move that is also a scene. The customization of the attack comes from its exported fields. See backend animation, animation, etc. There is all the juice. No matter longsword, claymore, halberd or whip, any melee attack can be designed from these nodes parameters if you have an animation asset. This achieved by having weapon hertz parameter track in the backend animation for the attack. See, 2 longswords hits are the same scene, they just have the different animations with different logical windows. Also, you can spot my skeleton animations no longer contain underscore rooted versions. Instead, longswords animations actually are rooted versions. Then where did root motion information go? It went into backend animations as well. It did cause some brain cells for me, because animation player isn't a no 3D and can have a position track leading to inability to just copy this track to there. I created a small def layer tool to engrave my root position tracks into this value track that, quotes, by coincidence is a vector 3 value track. I don't want to discuss it further. If you are brave, you can go to my GitHub and read this abomination of a method. Whew, I believe that's it. As you can see, nothing tectonic, but a lot of refactoring, and I believe I eliminated all technical debt I collected, at least what I can spot. This will be a nice starting point for our AI and networking journeys. Like, subscribe, make love not war. See you somewhere around 5th of July.